Thank you. Very happy to be here. Glad to see there's a lot of people here that are interested in the future, and particularly brain-computer interfaces. But before I begin, my mom doesn't think I have any friends. So I'm going to pull out my phone, and we're going to help her feel calm and say that I'm OK. So I'm going to do a selfie, and everybody could just raise their hands and say cheese at the count of 3, OK? 3, 2, 1, cheese! Nice. All right. So for those of you that know me, you might know that I'm a bit of a mutt. I do a lot of different things. I'm a filmmaker. I'm a neuroscientist. I dabble in entrepreneurship. I specialize in failing startups. The thing is, though, that as I was a kid, I wanted to be a physicist. I wanted to, the laws of the universe. How do things come together? If we understand physics, then we understand everything, right? Well, I realized that, wait, the laws of physics, they come from somewhere. I mean, they're universal laws, but we thought about them. They came, where does the thinking come from? And that's the brain. So then I was like, all right, I guess it is. The constellation that I care about is neuroscience. It's the brain. And so I went from cell biology to molecular biology to systems neuroscience and to then eventually cognitive computational neuroscience, which is what I do now, to kind of sort of understand how the mind works. And so before I begin, something that's a little bit taboo, but I think it's important to bring up, is that a lot of the medical advances that we know today that we sometimes take for granted came from animal research. And so I just want to take a moment to appreciate and be grateful for all the animal participants that helped lead to all the innovation that we have today, especially for brain-computer interfaces. So what is BCI? In 1973, this man called Jacques Vidal coined the term, and he said that BCI is like utilizing brain signals in a man-computer code as a means of control over external processes, such as computers or a prosthetic device. It's a handful. The way that I like to think about it, which is a little bit more general, a little bit more abstract, is a system that utilizes intentional or unintentional neural signals from the body or mind to control external processes. I think that's very simple. Anything that reads a neural signal that then controls something, whether it's intentional or unintentional. Last year, I was curious, how many brain-computer interface papers are coming out? So I wrote a little script to use keywords, the ones that you can see on the left, about how many papers, what's the volume? And even though research on brain-computer interfaces started before the 70s, and we're going to go over that, you can see that around the 90s it started picking up. And it's kind of roughly doubling every 5 years. And this is since I was updating a figure that I had made before, I didn't have enough room, so the barcode kind of goes up, because it's about around 4,000 within the last 5 years. But before we talk about brain-computer interfaces, it's probably important that I give you a tiny, tiny little Neuro 101 lesson on how neurons operate, because then that might provide a little bit of a layout of how things work and what exactly the brain-computer interfaces are reading. So our brain has approximately around 100 billion neurons, and the brain will send a signal down the spinal cord, then it goes through peripheral nerves to innervate muscles, and that leads to movement. How does that happen? How does it happen? So although neurons tend to have a variety of shapes and sizes, this is sort of the canonical shape, and it's made up of 3 components: a receiving end, a sort of bridge, a highway of information, and then the transmitting end. So the bridge, we call that the axon. And so when you have an excited neuron and it's like, hey, I'm active, it'll send a signal to a neighboring neuron. And the way it does that, it's active, it sends neurotransmitters. Those neurotransmitters then bind to these receptors. Those receptors then have these things called ions that have a positive charge flow into the cell. And then if there's a threshold that's reached, then they cause this thing called an action potential. And you can think of that as an electrical pulse. That electrical pulse then leads to more positive ions coming in to the cell. And they travel through the highway that I talked about, that axon, all the way to the transmitting end. And so this changing voltage from positive ions, which, by the way, they're also called electrolytes, that change is what a brain-computer interface is trying to identify. A voltage change in the solution of cells in our brain. And that voltage change, as ensembles of neurons work together, we can start figuring out, oh, so this type of change in this part of the brain is associated with this particular movement in this finger movement or this motion, leading to controlling a cursor or a prosthetic device. We can distinguish between different types of brain-computer interfaces between basically 2 categories. It's invasive and non-invasive. So the easiest way to describe it is that invasive just means, hey, I'm going to cut you open. There's going to be some surgery, there's going to be knives, there's going to be some blood. That's invasive. Then non-invasive is simply, we're going to make some skin contact. We're going to add some electrodes, we're going to put them to your skin or on the head, on the scalp. Sometimes the hair is an issue, depends on the system that you're using, but usually we can get some signal. And you can imagine that the farther away we are from the actual brain, the noisier the signal, which is why a lot of people really like invasive BCI, because you get really, really clean signal. You can get sometimes resolution of a single neuron activity. So EEG, FNIRS, they're on their way to becoming a little bit better, but the noise isn't great. So over here you can find two pictures, one of on the left, that's an EEG cap, and on the right, that's what it might look like. It's a little bit bulky for invasive BCI. What was that? Yeah, it's a DK1. Actually, yes, I think this is a Utah array, which is one of the very, 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 very first BCIs that ended up being commercial. And then we'll get into a little bit of the history of that company. So, sensors. So I'm going to go through some of the sensors that we see typically in invasive BCI. So there's basically two types, and we're going to see how they kind of change over time and what the future of that looks like. But the majority, if it's invasive, they're going to be rigid electrodes that basically puncture the brain, the cortical surface, and they'll have little sensors. And so they're arranged in some type of array form, and they record activities of multiple neurons. Sometimes some of these, like the neuropixels that you might see on the right, which is like a little bit longer, that can sometimes do single neuron resolution. Then there's also things that we do in electrocortical echography, which is also termed as ECOG. Those are still invasive, but a little bit better because they don't penetrate. You don't cause any scar tissue because they just rest at the surface of the cortical of the brain. So how did we get to this point? The point where we can just cut someone open, cut an animal open, put some electrodes, and then decode. How did that happen? We have to go back in time. So we're going to go down a little bit of a time machine and check out how did this happen. A thing that I really, really need to mention here is that the majority of you probably, well, okay, so how many of you have heard of Neuralink? Have you heard of any other BCI company? Keep your hand raised. Okay. Yeah, Neuralink is just really good at marketing. There's a really, 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 really deep, long, and rich history and legacy of tons of BCI research before Neuralink, dating back many, many years. And so this is not a comprehensive timeline, but it kind of highlights a little bit of the landmark moments in the world of BCI. So we're going to go back in time. We're not even going to go to the last one. We're going to go 5 years before the last one, in 1986, yeah. And so in 1986, during this time, it was also considered like an era of vitalism. Philosophers, scientists, they were all really, really curious about, what makes a difference between non-living and living? What's the difference? So they thought, there must be a vital spirit, a vital force that animates the living. And so scientists were trying to figure this out. There was a particular one a physician called Luigi Galvani. And Galvani, he was he was conflict aversive. And one day he was just dissecting some frogs, and he had like a little device that could create static shock. And all of a sudden, accidentally, a little bit of shock innervated the frog legs. Those frog legs wiggled, and he was like, oh, whoa, what's going on? So then for the next 5 years, he's just researching, doing experiments, identifying, what is this thing? He published some papers, and he was like, hey guys, I found it. I found the vital force. I found the vital spirit. It's called animal electricity. And he got a lot of people interested. He even published the first papers. He did it at his own cost and distributed it around his little science friends. One of them was Alessandro Volta. And Volta, you might know from voltage, volts. He was very interested in this. He was like, what's this thing, this animal electricity? I don't think it's animal electricity. I think there's an error in your work. It's the metal. The metal is the thing that's innervating these frog legs. And so for the next 5, 6, 10 years, there was an intellectual battle between Volta and Galvani. Galvani, as I said, he's a little shy, so he didn't publish with his own name. He sometimes published responses to his critiques anonymously. So Volta got so obsessed with this animal electricity thing, and he started doing his own experiments, trying to prove Galvani wrong, where he started mixing metals together, stacking them on top of each other. And that ended up becoming the voltaic pile, or what we know now as the electric battery. Afterwards, Giovanni Aldini who is the nephew of Luigi Galvani, he was also obsessed with animal electricity. And so he is famous for finding corpses and trying to reanimate them with electricity. One such case, someone had recently been hung or beheaded. He grabs a corpse, takes it to a show, very macabre, I know, and then literally tries to innervate it. People would go and see these things, and it was like a big entertainment thing. A few years later, Percy Shelley, Mary Shelley, and Lord Byron, some of you might know Lord Byron being a poet, they were all hanging out. They're just like chilling, probably smoking weed or something. And then they were like talking about, oh, all these Giovanni Aldini experiments, reanimation, animal electricity. Those conversations ended up what became Frankenstein, the book. And so Giovanni Aldini or Luigi Galvani may have been the first or actual original Dr. Frankensteins. So it's kind of crazy to think that just one tiny little accidental experiment where a shock innervated the legs of a frog ended up leading to modern neurophysiology, ending up leading to a very, very important science fiction book that we all know, and to the electric battery. So that's all in 1786. So now let's zoom past a little bit in the future. Around the early 1900s, animal EEG was starting to be used, but what about human EEG? So in around early 1900s, a man by the name of Hans Berger was in a military exercise. He was riding his horse, probably carrying some rifle. Men were marching next to him with rifles. Horses were carrying cannons along beside them. When all of a sudden, his horse leaps into the air, dropping him to the ground, and all of a sudden there's a horse pulling a giant cannon and it's about to crush him. Miles away, at the same exact time, his sister had a premonition. She was like, oh no, Hans is in danger, father. We have to go, send him a message. Urges the father to send a telegram immediately to him. And then later on, as he recalls this event, he thinks, oh, there might be something very special about the universe, a way that we can communicate across space and time. And so he became obsessed with telepathy. And with telepathy, he started scanning people's brains. And so he actually termed the coin EEG, I can't even say it right now, and actually was able to record the first alpha waves. To date, he's kind of credited with EEG, even though that kind of that happened before. So 1963 is actually a very particularly interesting year and one of my favorite years for BCI. Because massive advances were being made by Dennis Alb-Fessard in neurophysiology. So she actually pioneered a lot of the work that we know now as microelectrodes, the things that we use that I was talking about with BCI. And she was able to record from mammalian brains and also identify regions of the brain that were associated with movement disorders such as Parkinson's. That same exact year, Natalia Bakhtereva out in Russia was probably is the first reported moment for deep brain stimulation for movement disorders such as Parkinson's. Unfortunately, maybe due to a sexism or like the fact that there wasn't a lot of readership in Russia, a lot of that work wasn't immediately known, but she was very important. Also in 1963, something crazy happened that to this day just blows my mind. In 1963, there was this guy called Jose Delgado. He created a radio receiver and transmitter and had done surgery on the bull, and then was able to stimulate wirelessly the bull's thalamus and other parts of the brain that are associated with movement to stop it mid-attack. And finding information about this is actually a little bit difficult. But I was able to find the PBS documentary where you see Jose on the left, on his left arm, he's holding the radio transmitter. It's hard to see here, but there's like these antennas coming out of it. And right there, he's stopping the bull. And there's even an article in what year was this? Like 1963 or 64 when it came out, talking about this crazy thing. It's kind of wild. This is kind of forgotten sometimes, but it's one of the earliest wireless BCI. It's crazy. All right, so 60s and 70s, great era, but in the interest of time, I'm only going to talk about two more in this time period. So Edmund Doohan was a physicist, and he was doing research at Brandeis University and also the Air Force, and he was also interested in EEG, and so he built his own device and was able to record alpha waves. And actually, this actually might be the first version of BCI controlling something like a light bulb. So over here, the alpha waves were able to be used into on and off states to turn a light on or off. He was able to also use this to do Morse code, but probably not super efficient, not super fast. In the same university, Brandeis University, there was an avant-garde composer by the name of Alvin Lucier. And Alvin also played an instrument just like Edmund. Of course, he was an avant-garde composer. And they would hang out. And Alvin said, hey, can I borrow your equipment? And Edmund says, yeah, please, please, please. And so in the first recorded music BCI in 1965, we have brain to music. And I have a clip here from a recreation of it in 1988. And in 1988, actually, in this picture that you see here, that man putting the EEG headset on Alvin is none other than John Cage, another famous avant-garde composer. So over here, if the audio is working, that's him, Alvin. He's concentrating really hard. He's sitting down, and you can see there's a headband recording EEG. What's going on right here is that there's the EEG signals are being bandpass filtered because there's a lot of artifacts that happen. That bandpass filter is then being sent to an amplifier and then further amplified by a mixer that was in the room. The signals are being sent to loudspeakers, to amplifiers that were then pushed on top of the instruments that they needed to innervate. So at this point, it's not like a motor is being used to move instruments, but the vibrations caused by those frequencies are vibrating the instruments. Still, very, 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 very cool. As you can see here, you can see the speaker on the snare drum. Feels like something from X-Men. Okay, so let's move forward to some other important milestones. So in 1998, there was a neurologist, Philip Kennedy. He was very important. He was also an inventor. He did a lot of really important work for BCI. So he was at Emory. He actually was one of the first to do a BCI on a human, invasive BCI in 1998. But like the sort of where you can find this information is very, I think it was a temporary BCI. It was just for a moment. But then 1998, the first person that's considered as the first BCI person, Johnny Ray or JR, was able to control a cursor. So Philip Kennedy is a very interesting man. He, like many before him, was very obsessed, as a lot of people end up becoming in this field, just obsessed with like the brain, kind of like the constellations, what's going on. So much so that after he ran out of funding, unfortunately, he couldn't get any more grants. He still needed to do BCI. He still needed to understand. He still wanted to work and help people with paralysis. So he went to Belize and underwent surgery himself to get one of these things implanted. And he might be the only scientist who has gotten himself implanted with a device that he used on other people through surgery and recorded himself for 80 days before he had to go back and get it removed because the sutures were opening. Very, very interesting man. I think there's even a documentary that has made about him that I should check out. Yeah, so another very important person that I think a lot of people overlook is Miguel Nicolelis. And he did a lot of really, really, really fascinating work with BCI. So in 2003, and even before this, he was doing work with monkeys where they were able to use he was scanning for motor cortex using invasive electrodes and having the monkey move a controller. And then eventually, you just remove the controller because now you've been able to read out the signals that are associated with particular XY movements on the screen. So he was able to teach his monkey to use to move a cursor on the screen without having to use the actual control. He also was able to do this in a way where, like, instead of controlling the cursor on the screen, the monkey was controlling a robot arm that was then controlling the cursor on the screen. And not just that, he also then did this crazy thing where, like, he had a monkey control an exoskeleton, basically not an exoskeleton, a robot that was thousands and thousands of miles away, all the way in Japan, using BCI. So we have the first international BCI, wireless BCI. And this guy, nobody really knows about him outside of like people very specifically in the BCI world. Let's move forward to the 2010s. This is one of my favorite demonstrations of brain-computer interface work. So this is by John Donahue's lab. And right here, we're going to see a woman controlling a robot arm to provide herself with a drink. And one of my favorite parts about this video, I'm just going to move a little bit over here. As you can see, she's thinking, that right there is a Utah array. As you can see, it's invasive, but it's a little bulky too because it sticks out of the head. Obviously, we're going to talk a little bit about what the future is going to look like, but this is not super practical long term. And I'm going to zoom past because there's a particular moment that after she takes a sip and then puts it down, there's a smile of success that is just, there you go. It's just beautiful. Yeah, this is one of my favorite demonstrations of BCI. And actually, just last year in 2023, they're doing these things now called brain-spine interfaces. And this is really, 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 really cool work. So the idea is, if you have a severed spine, what you can do is, hey, okay, the spine's still, I mean, the nerves and the parts of the spine are still working. It's just like the connection's not super great. So what we can do is like, let's put electrodes on motor cortex. Let's learn what motor movements are for this particular person. And then, hey, let's put another set of electrodes, but let's put it in the part of the spine that still innervates the legs. So instead, we're going to have a BCI that reads out signals and then bridges them through another electrode to simulate the legs. And this person can now walk again. And as you can see, I'm going to show yeah, here we go. So he's walking, and testing this is that you can actually just stop the connection, right? You can say, hey, we're going to stop stimulating the legs. And over here, as you can see, he's trying to walk, but he can't because it's not on. And then when we turn it on again, not me, but the experimenters, he's able to. So this can lead to improvement in walking over a lot of therapy, but you can see it's already bringing possibilities back to the people. All right, so I've been talking about a lot of these things. Okay, I'm running really out of time, so I'm going to hurry up. So everybody's thinking, oh, wait, what about Neuralink? What about these other companies? So yeah, Neuralink is doing pretty cool stuff, but they come from a large history of other people doing the very same things before them. It just so happens that they're really good at marketing and they can make it really sell. I will say that one thing about Neuralink that's really cool is that they have a robot that does the surgeries. So when we try to do, not us, but neurosurgeons are doing brain surgery, craniotomies, the brain moves along because there's blood's pumping into your body, so it wiggles. So trying to make sure that you don't puncture a vein is very important. There's other companies like Synchron that are also trying to do minimally invasive BCI. So they insert through the jugular vein a device that's a little bit of a mesh that goes all the way into one of the veins that then spreads into the brain. And so it's very invasive. It just requires an incision, but it goes up. They're doing cool work too, also for help paralysis. There's also Precision, which is actually from a co-founder from Neuralink that is working on this as well. And then what they're doing is they're doing a little bit more of a flexible sort of a set of electrodes, but instead of like doing a full craniotomy, you just do a slit and you slide it in. And then you'll see here, if it shows up in the video, there's going to be a moment. There you go. So you can see you just slide it in. Very cool stuff. Okay. But what is the future? The future is not going to be rigid electrodes. That's where people come from. The problem with rigid electrodes, like the ones from the Utah array, the ones that I showed you from the first experiments, those are rigid. They cause scar tissue, and neurons stop, like there's movement, and so the neurons, you have to pick up new neurons, you have to retrain. Although this is still going to be a problem with all BCIs, but the future is going to be flexible electrodes, meshes or things that sort of move to the contours of the cortical surface. So the same people that ended up owning the Utah array are also moving into flexible BCI. So they have this thing, they announced it like a year ago, but I haven't seen any news about it, except that just recently, I just learned this like the other day, the majority shareholder now is a crypto company. They invested like 200 million, so now a crypto company owns BlackRock Neurotech. That's interesting, possibly cool, possibly not cool. But the question is, do we really need invasive BCI? As I've given you tons of examples, it's very intense. And the answer is like, I'm not sure. Control Labs, which is bought out by Meta, they have these like really cool gloves that allow you to just EMG, so it's detecting signals from the nerves that send motion to the fingers, and you can do a lot of stuff. I've seen videos not included here where they bring back the ability to type and use their hands in VR for people that don't have any fingers. So very, very cool. Colleagues in UT Austin are doing word decoding, very cool stuff. Basically, it's not to the point where you can do single-level word decoding, and this doesn't even require doing anything in motor cortex. This is distributed representations about how language operates semantically, and they're able to kind of get the gist of what you're thinking. So if I say, I really like McDonald's burgers, the decoded message might be, I like food, or I like burger, which is still pretty good. It's just a gist, but at some point we will get, and they have issues with pronouns as well. So over here on the left, you see a scene image. And then on the right, you have a reconstructed image. So my buddy, he's been working on this. A lot of other people are working on this type of thing, but it's called image reconstruction, where you try to use brain signals to reconstruct the image. I'm going to be done. I'm going to move. So this brings up a problem. So what about like ethics, the privacy, the agency? What are we going to do about these things? Like as we give away most of our privacy, we're also giving away a little bit of our agency. So I see a future where potentially, instead of like having, maybe we don't need all these BCIs exercise, getting stuff from our brain. Maybe we just need like a smartwatch, like the one pictured here. I made this demo for a video that I made 2 years ago, where you can imagine like going into a store is like just putting on, you put on your smart glasses, you turn it on, it's like going into a website. You get a little terms of policy where it says, hey, we're not going to do any eye tracking, we're not going to do any of that stuff. We just want to get access to the cameras in front of you so we can overlay augmentations into space. You have 2 wearable smart glasses that don't even need eye tracking and a smart watch that does EMG signaling. That's kind of a future. I care so much about ethics and the privacy and things like that that I started a new conference called Neuroethics and the Future of Reality. I highly recommend people to check it out. We're looking for funding, so if you know anybody that has a lot of deep pockets, it'd be really super cool to tag him along and maybe like bring him up to me or her, because money is important and nice. And to make stuff like this happen, where we bring people together, is really important. So yeah, thank you so much for coming here, and I'm glad all of you enjoy BCI and are excited about the future.